Okay, so the next thing we want to talk about with sequences is classifying them based on some of the properties they have, some of the properties that they have. So there's four different definitions here that we can give to a sequence based on its properties. Okay. So these aren't things you have to memorize, but sometimes in the homework they'll ask you to do this classification. And it's kind of leading up to a big result uh, as well, a big result on convergence of a sequence. Uh, that does kind of matter a little bit. So here's the idea. So first off, we begin with our first definition. Say a sequence is increasing if, as you progress through the sequence, the terms keep getting bigger, right? All right, for all the n on consideration. Sequence is increasing if an plus 1 is greater than for all n under consideration. We go further and say that a sequence is not decreasing if we require each value to be either greater than or equal to. All right, that's called a non-decreasing sequence. So it allows it to take on repeat the same value in the sequence. So that's basically increasing, plus you can also just be the same value. Okay, that's called a non-decreasing sequence. We continue and say that a sequence is decreasing if the values get smaller as you progress through the sequence. As you take on bigger and further to the right in the sequence, the values keep getting smaller. Right? That's called a decreasing sequence. And if we allow the inequality less than or equal to, then it becomes a non-increasing sequence. It becomes a non-increasing sequence. So these four definitions, increasing, decreasing, it kind of makes sense. The problem, when we add the inequality in, increasing becomes non-decreasing, and decreasing becomes non-increasing. Non-increasing. Okay. So we continue now by defining a sequence which is called monotone or monotonic. Right, a sequence is monotone or monotonic if the sequence is either always non-increasing or always non-decreasing. Okay. So again, we allow for the possibility of repeating values. That's okay. Right? And that's our definition of what's called monotone or monotonic. And we have one final definition here, and that is that a sequence is bounded if there's some number m such that the absolute value, because science could be negative, right, is less than or equal to m for all I greater than n. Right? At some point, beyond a certain point, right, everything in your sequence beyond a certain value n, everything is always smaller. It's okay if some of your initial points were bigger than that, but after that point, they're all smaller. They're all smaller. Okay? And so the big result is this, that every bounded monotone sequence converges. So if our sequence is either always decreasing or always non-increasing, or always increasing or non-decreasing, either one, and it has an upper bound, right? You can't get above a certain point, then this thing will converge, it turns out. That's actually a big result in the study of sequences theory-wise. For us, we're just going to kind of notice a few things about it, okay? That we're just going to kind of leverage that idea to talk about whether or not a sequence converges. For the most part, for us, we're just going to stick to, when it comes to the question of convergence for a sequence, we're just going to stick to the question of, well, let's compute the limit. All right, let's compute the limit. And that's great with a sequence. But later on, what we're going to do is we're going to take sequences, and we're going to start adding up all the terms of a sequence to produce a new sequence. Right? To produce a new sequence. And that's something called series. And so some of these results about bounded and monotone kind of matter a little more for that kind of stuff. But I want to show you one example of using this to check, to show that something does converge. It doesn't actually show what it converges to, but it does guarantee convergence. So let's consider the sequence here. 1 plus 1 over n. Okay. So first of all, this thing is bounded. This is bounded because a sub I, every term in that sequence, is never going to be any bigger than 2. All right, first value you plug in, 1. 1 plus 1 over 1 is 2. Then it would be 1 plus 1/2 would be 1.5. 1 plus 1/3 be 1.3 repeating. 1 plus 1/4 be 1.25. Right? We can agree that this is bounded. This is bounded. What else can we realize? Well, if we look at the derivative of that function, the underlying function, 1 plus 1 over x, its derivative is negative 1 over x squared. Right? Its derivative is negative 1 over x squared, which is always less than 0, because when you square x, that's positive, but you have a minus sign there. So this thing for positive values, actually for all values of x, where it's defined, this thing is decreasing. Of course, if it's decreasing, it's also non-increasing. So therefore, we know that this sequence converges. And without investigating what it actually converges to, we do know that it has to converge.